Hello, Honors Algebra students. Here's a special video for you, and maybe I will show this to level 2 kids. So I'm just going to shout out to a couple people here. Let me think. So I haven't shouted out to Adam yet. Adam, doing good work. Keep it up. Keep it up. Let me think here. Who else do I need to shout out to? How about Caitlin? Caitlin, I loved how you got help during study hall, and then you still wanted to come in at lunchtime. A lot of times if you come in for help when it's a small group, I can show you things that I can't necessarily do in a large group. So I'm glad you came in, and I hope you're not gun shy of coming in more in the future. All right, in case you're wondering, it is 3:12 in the morning. I went to bed kind of early last night, got up and made this video. So, yeah, that's not a mistake on my computer if you happen to notice it. Anyway, we're just going to do a little recap video here about lesson 6 and 8 that we've been talking about. One, we can think about numbers in many different ways. And remember that we can think about the number 3,724 as 3 1,000s plus 7 100s plus 2 10s plus 4 1s. Oops, 1's not 10, sorry about that. And I don't know if you realize this yet, but I'm trying to get you to think about things like polynomials. For example, we could think about this as 3 times 10 to the third plus 7 times 10 squared plus 2 times 10 to the first plus 4 times 10 to the 0 power. Okay, well then that's no different than saying, hey, what if x equals 10, right? Or what if 10 equals x? That would be 3x cubed plus 7x squared plus 2x plus 4, which of course is a polynomial of degree 3, or a cubic polynomial, right? A cubic polynomial from our naming. All right, so when we think about these numbers in different ways, it makes it a little bit easier to do multiplication problems. Now, some of you may have noticed I've written the same problem down twice. I'm going to do the problem first by breaking it up into squares and rectangles. Then I'm going to break it up. I'm going to do it differently using the distributive property. So right here, this is one side of my rectangle. So I need a length that is x, and then 5. So therefore the side there is x plus 5. And I guess that's too big of a mark. I'll just make a little mark. Maybe instead of doing that, I should actually use line segments. It'll look a lot easier for you friends at home. All right, so we'll label this part of it x, put a little mark, and we're going to make that part 5. Okay, now the other side, I'm going to need a side x, so it's going to need to be that long, just because I want to try to make it squarish. Okay, looks like I'm going to run into a problem here. Hold on a second. I'm going to take this and just move it on down a little bit. All right, there we go. Now I need an a, so this is x. Put a little mark. I leave a little segment for a, and how big I make these segments is really up to me. Okay, and so that'll be a, and then I need a segment that's 2 units long. So actually, I guess I should just do this. It'll look prettier. Hold on a second. There we go. All right, so now I'm going to finish drawing my rectangle. I'm going to need to go all the way here, here, and here. And of course, if I don't have it exactly right, I can adjust them a little bit. Looks like they're pretty close. So I'm just breaking this rectangle, creating this rectangle by breaking it up into pieces. And now I'm going to find the area of each of those pieces, and then I will add them all together. So the area of this square would be x squared. The area of this rectangle would be 5x. The area of this would be ax. We tend to write things alphabetically. Then we have a 2x, we have a 5a, and we have a 10. So the area of this entire rectangle is going to be x squared plus 7x plus ax and plus 10. Okay, that is the simplified form. You may have come up with some other answers. You may have come up with x squared plus 7x. No. Oh, I'm sorry. Here's what I wanted to do. Plus x times the quantity of 7 plus a, or a plus 7. Okay, plus 10. They are synonymous. You notice I've got x terms here, right? But this guy here is also an x term. And so I kind of undistributed the x. I can think about it that way. I personally like this answer best, okay, because it's simplified, but there's nothing wrong with this answer. Mathematically, it's the same thing. Okay, so let's see how I'm going to do this differently. I'm going to do it without drawing a picture. Now, you need to be able to understand both parts. Well, if this said x times the quantity x plus a plus 2 plus 5 times the quantity of x plus a plus 2, you would distribute this x, right? And you distribute the 5. So you're going to get x squared plus ax plus 2x. And then you're going to get plus 5x plus 5a plus 10. And then when you combine like terms, you would get x squared plus ax plus 7x plus 5a plus 10. All right? Now, you could have done it in one step. You could have taken the problem just like this. Hold on, let me move it down here. And just double distributed right from the get-go. You could have said, hey, I'm going to distribute this x. And then I'm going to distribute the 5. Okay, because that's what I essentially just did. I just broke it up into 2 distribution problems. Okay, it doesn't really matter which way you do it because you're doing the same thing. So when I distribute the x, I get x squared plus ax plus 2x. And then when I distribute the 5, I'm going to get 5x plus 5a plus 10. And you can see when I combine those like terms, I will get this same answer. All right, 3 different ways to do the same problem. You need to be able to do it this pictorial way, and you need to be able to do it one of these 2 ways, either the red way or the green-blue way, okay? All right, so how about when you get to a problem like this, hold on a second, I need some more work to work. Really wish I could pause this video. There we go. Giving myself room to work. That's all I'm doing. All right, let me move that down. Let me grab that and move it down. And that should be enough room to work. Okay, so to do this problem, it got kind of confusing to do the 3-dimensional one. the other day in class, didn't it? So I'm first of all going to take it as a problem like this: x plus y times quantity of x plus a. And I'm going to double distribute. I'm going to multiply here and here. And then I'm going to distribute further here and here. All right, so when I do that, I'm going to get x squared plus ax plus xy plus ay. Okay? So now I'm going to multiply it by this other term, p plus q plus 3. All I have to do is distribute the x. I'm going to go here, here, and here. Then I'm going to distribute the ax. Then I'm going to distribute the xy, and then the ay. All right, so let's see here. It's going to get a little bit long. I'll try to organize everything. So the x squared, so I'm going to get a px squared plus a qx squared plus a 3x squared, right? Then I'm going to get an apx, and then an an aqx, excuse me, an aqx plus a 3ax. Now I'm ready to distribute the xy, and so I'm going to get a pxy. Then I'm going to get a qxy. Okay, then I'm going to get a 3xy. I'm not seeing any like terms, so I'm just keeping this puppy going. Plus, now I have to do the ay, so I'm going to get an apy plus an aqy plus a 3ay. And there you go. There is your polynomial. All right, it's kind of long, but it's not really difficult. You just have to remember to do all the parts. One last thing I want to address here is what happens when you multiply a radical by a radical. Yeah, I've just used a term you've never heard before. This isn't called a square root, it's called a radical. Okay, and you'll see more about that later. Remember that the square root of 25 does not equal 5, it equals plus or minus 5. Okay, but there are some numbers that we can't take the square root of. We can guesstimate them. 21 is not a perfect square. And this number is actually called irrational. Yeah, it's just like pi, that very famous irrational number. As a decimal, it goes on forever without repeating. There is no number times itself that equals 21. But what happens when you multiply a radical times a radical? Well, let's check it out here with something easy. I've got rad 9 times rad 9. Okay? Well, some of you could go, hey, this is 3 and this is 3, and so therefore the answer must be 9. Well, that's interesting, isn't it? I mean, if you look, you had the rad of 9 times the rad of 9, and you just ended up with 9. Huh. Well, let's try that again with 36. Okay, rad 36. So we're going to have rad 36 times rad 36. And that is going to be 6 times 6, which is 36. Oh, look at that. It happened again. How are you going to do rad 2 times rad 2? Because you don't know the square root of 2. No, you don't. I know some of you are thinking, yeah, I do. It's 1. You are incorrect. I know you weren't thinking that, Laura, because you know that the square root of 2 is an irrational number. Absolutely. All right, so how am I going to do the square root of 2 times the square root of 2? Well, that is the same as the square root of 2 times 2, which is the same as the square root of 4. And since we're only dealing with positive square roots for radicals, I think I forgot to mention that, sorry, we're going to get 2. But if you want to give me plus or minus 2, I would be very proud of you. Okay, so plus or minus 2. There you go. So, all right, square root of 5 times the square root of 5, or rad 5 times rad 5 is going to be 5. the rads, in effect, cancel each other out. Yeah, they cancel each other out. We'll talk more about that later and why that happens. There's so many reasons for it. It's actually pretty simple. For right now, what you need to know is that rad 5 times rad 5 is 5. Rad 5 is an irrational number because 5 is not a perfect square. Okay? So rad 121 is rational, but the rad of 120 is irrational. You can only approximate it with a decimal. All right, that's it for today's video. Mr. Lawrence signing off. Have a good night, everybody.